Hello, I'm Dan Sullivan, and this is an overview of the video course Alan Turing's Wonderful Machine. Alan Turing was a leading mathematician of the 20th century. The recent popular Hollywood movie, The Imitation Game, highlighted his work decoding secret German Enigma messages in World War II. Many credit Turing with shortening World War II by more than a year and saving hundreds of thousands of lives. It's hard to think of anything more important than Turing's work in World War II because of its impact on that war. But this course isn't about how he decoded those Enigma messages. It's about a paper he published in 1936. The paper was published in the Proceedings of the London Mathematical Society and is titled Uncomputable Numbers with an application to the Entscheidungsproblem. Uncomputable Numbers was a groundbreaking mathematics paper that was forward-looking and fascinating, and it also presents a fundamental model of computing that continues to this day. This course is a programmer's view of the content and impact of uncomputable numbers, and this video is a taste of what is in that course. The computable numbers the title refers to are the real numbers, and the paper is about the capabilities of a non-mathematician, given a set of directions, to compute real numbers using pencil and paper. Uncomputable Numbers provides the mathematical basis for how real numbers are computed with paper and pencil or otherwise, and also clarified questions about the logical basis of mathematics itself that had been plaguing mathematicians for years. The latter here, about the basis of mathematics, is what the Entscheidungsproblem part of the title is about. Entscheidungsproblem is a German word that means decision problem, and was probably the most groundbreaking part of the paper when it was published. We'll see more about it shortly. But if you're watching this course, you're probably involved with computers or programming, and think of the Turing machine when Alan Turing comes to mind. You might be wondering, where did the Turing machine come from? Well, it came from uncomputable numbers, but Turing just called it an automatic computing machine. The term Turing machine appeared later when others used it to refer to what Turing called an automatic computing machine. The automatic computing machine is the model of computation that Turing created and then used to reach the conclusions he did about computation and the logical basis of mathematics. Keep in mind that Turing's automatic computing machine wasn't a design intended to be implemented with mechanics or electronics. It's a model used to reason about and to demonstrate the computation of real numbers. Turing's automatic computing machine also provides a benchmark for the computational capabilities of any computer to this day, and is also a model of what we think of as a computer, that is, a stored program general-purpose computing machine. Turing was a graduate student at the time he published Uncomputable Numbers. Soon after it was published, he and Alonzo Church, his graduate advisor, made the statement that no computer, whatever it was made of, would have computational capabilities beyond the benchmark set by Turing's automatic computing machine. This is called the Church-Turing thesis. Note that in mathematics, a thesis is an unproven statement thought to be true. In fact, to this day, it has not been proven true, but so far, no computer has been developed that has pushed beyond this benchmark. All of this in a paper written about 80 years ago, when the only things we, the programmers of today, might vaguely consider to be a computer were card sorters and mechanical calculators. Wow! The thing that spurred Turing to write the paper were computers. Wait a second, didn't I just say there wasn't anything we would call a computer in 1936? Well, no, not what we would call computers. But up until about 1950, computer was a job description, like baker or plumber. A computer was a person, not a mathematician, who was given a set of directions, paper and pencil, and maybe a mechanical adding machine. Their job was to follow those directions to compute some real numbers. For example, the military used computers, that is the human kind, to make numeric tables used to aim large guns. Mathematicians were curious about the capabilities of these computers. For example, was there any real number that a human computer could not compute? Now, most of us are involved with computers and programming, so you might be thinking of the limitations of floating point numbers. Mathematicians at that time were not thinking about floating point numbers. That concept did not exist in 1936. They meant the mathematical concept of a real number, which, by the way, might require an infinite number of digits to write it down. So at first glance, you might think that a computer could not compute all of the real numbers because it would just take forever to do. But mathematicians didn't care about forever. They just wanted to know, even if it took forever, was there any real number a computer could not compute? They were interested in a theoretical capability, not a practical one. So now that we know it can take forever to do our computation, it seems like we should be able to compute any real number. Well, it's not that obvious, and that's not a proof. So one of the major things Turing used his automatic computing machine to do was to see if he could find any real numbers that could not be computed. The other major thing Turing used his automatic computing machine for was to solve the Entscheidungsproblem, or in English, the decision problem. David Hilbert was a mathematician who was a major proponent of putting mathematics on a basis of logic. After Gödel showed that that would never be possible, Hilbert and other mathematicians wanted to know if a computer could figure out if a logical statement was one of the ones Gödel showed could be constructed. That is, they wanted to know if a computer could decide if a logical statement was provable. That's the Entscheidungsproblem, or decision problem, that Turing ended up solving with his automatic computing machine. Here's a simple example. A is 3, and B is 9, and A is greater than B. Of course, this statement is false, but in a more involved statement of logic, that could be harder to see. But before Turing published Uncomputable Numbers, the mathematician Kurt Gödel proved that, in simple terms, it was possible to construct a statement of logic that could not be proved to be either true or false. This, along with some other things, pretty much upset the idea that all of mathematics could be based on logic. After that, though, mathematicians wanted to know if a computer could figure out if a logical statement was one of the ones Gödel showed could be constructed. That is, they wanted to know if a computer could decide if a logical statement was provable. That's the Entscheidungsproblem, or decision problem, that Turing ended up solving with his automatic computing machine. Turing based his model of computation, that is, his automatic computing machine, on the directions a computer, the human kind, would use to compute numbers. Here is a made-up set of directions that could be used by a computer. Don't try to read them. The individual directions are not important for what we want to look at now. The first thing to notice is that these directions are just some English prose. How are you supposed to reason mathematically about prose like a rose by any other name is still a rose? Is that saying you can divide by 0? That's just a joke, of course, but it's just that prose can be very hard to interpret. Turing looked at prose instructions for a computer and broke out the key features of them to make his automatic computing machine. There is also something that is not here that is notable. There is no title. There is nothing that says what these directions do. They are meant for a computer, that is a non-mathematician, to follow, and that's all. For the record, though, these directions compute the sequence of digits that are produced when you divide 3 into 1. Of course, that's just 33333 and so on into infinity. However, these instructions do not compute the value of 3 divided into 1. That would require keeping track of a decimal point and would make these directions much more complicated. As is, the directions just produce a sequence of digits. Actually, Turing ran into the same problem. Uncomputable numbers is about computing real numbers, and most of those numbers need a decimal point. But all of Turing's examples, explanations, and proofs are about sequences of digits with no decimal point. In fact, Turing's automatic computing machine could only produce the digits 0 and 1. Turing points out that his automatic computing machine could use all 10 digits and a decimal point, but that would make things more complicated and harder to work with, and weren't necessary to show what he wanted to show. He used a technique often used in mathematics when you run into a problem that is just too detailed and tedious to work with. You prove that it is the equivalent of another problem that is much easier to solve, and then solve that other problem. And that's just what Turing did. He showed that by producing sequences of zeros and ones, he could prove everything he needed to prove about real numbers and the Entscheidungsproblem. Another thing about these directions is that there are only 20 of them. That is, there's only a finite number of them, but they produce an infinite sequence of digits. Turing would say that the sequence was satisfactory because it is infinitely long. he considered a result that was just a finite sequence of numbers to be unsatisfactory. Turing was making this distinction in a mathematical sense. Only infinite sequences of zeros and ones were of use to him in proving things about real numbers. Let's look at the basic operational details in these directions. First of all, we need a person to carry out the directions. That's the computer. The directions mention things like write the number. If we're going to write, we will need something to write on, and the directions mention using paper for that. Of course, to actually write, we are going to need something to write with, too, like a pencil. And in some of the directions, the computer has to erase things from the paper, so our pencil needs an eraser. Now, for what is probably the most important operational detail of these directions. Turing noted that his automatic computing machine was based on a finite number of directions, just as directions for a human computer are. However, sometimes directions are inherently sequential. You just do one after the other until you get to the end and then you're done. For example, to make a cake, you put eggs in a bowl, then add sugar, then add flour, and so on. Then mix and pour that into a pan and then cook, and that's it, you're done. But a finite set of sequential directions like this can't produce a satisfactory result, that is, an infinite sequence, unless some of the directions are used over and over. Turing pointed out that when a computer completes the things an individual direction tells it to, it then uses its power of observation and its state of mind to decide what direction it should perform next. Driving directions are a simple example of this. While driving, your state of mind might be to keep driving to the next intersection until you see a sign that says exit for 128 south, in which case you take that exit. However, once you take that exit, your state of mind changes. For example, to keep driving to the next intersection until you see a sign that says exit for Route 20 west, and so on. So, with the completion of each direction, your state of mind may change. Each of the directions we have for our computer sets its state of mind. By default, that state of mind is to do the following instruction once it completes the current one. But some instructions tell the computer to observe something on the paper it is using. For example, if the number marked with D, and based on that observation, choose the direction to perform next. Turing pointed out this state of mind in computer directions and made that a key feature of his automatic computing machine. Turing invented what we now call a state machine. Now that we've seen the key features of directions a human computer would follow, let's take a look at one of Turing's automatic computing machines, run it, and see where the features we just looked at appear in it. An automatic computing machine itself is very simple. There are only 4 components that make it up. But keep in mind, it's a mental model and not something that is necessarily intended to be physically built. First of all, it has some paper, as the human computer did, but it's in the form of a long paper tape, not sheets of paper. The tape itself is broken up into squares, much like movie film is. Each square in the tape can hold just a single symbol, like a 0 or a 1, a letter, or it may be blank. A printer and a scanner are 2 more of the components, but they are built together into a single mechanism. The printer can print a single symbol in the square that the printer scanner is on. This printer operates a bit differently than you might expect. What it prints replaces what is in the square, it doesn't just overprint it. So it can replace, for example, an X with a D, or even print a blank. This printer is the equivalent of the pencil and eraser used in the directions for the human computer. The scanner is used to observe what is in the square the printer scanner is on. The automatic computing machine always makes a decision about what to do based on the symbol in the square the printer scanner is on. This scanner is the equivalent of the power of observation in the directions for the human computer. The printer scanner mechanism itself can be moved along the tape, but only 1 square at a time, to the left or right. Note that in an automatic computing machine, it is the printer scanner that moves, not the tape. The last component are the directions that the automatic computing machine will follow. Here is an example. Turing calls this a table of states of mind, and it lists all the possible states of mind, B, O, Q, P, and F, that this automatic computing machine could have. Today, we would probably call this table a program, But that use of the word program did not exist in 1936, so we'll stick with Turing's terminology. These states of mind are the equivalent of the ones we saw in the directions for the human computer. Each state of mind has one or more directions associated with it, and the automatic computing machine chooses which of these directions to follow based on the symbol being scanned. That is, the symbol in the square the printer scanner is on. For example, in the state of mind P, if the schwa symbol, that's an upside-down E, is scanned, the automatic computing machine moves to the right and then changes its state of mind to F. This F is, in Turing's terminology, the final state of mind for this direction. That is, it's the state of mind this direction will finally end up in. The table we are looking at in this example is used to produce a sequence of expanding subsequences of ones, like this. You see 1, then you see 1, 1, then you see 1, 1, 1, and so on, to infinity. Turing needed a way to run his automatic computing machines, but the only thing he had to work with were his mind and a fountain pen. So he came up with a notation that he used to track an automatic computing machine from one direction to the next, sort of like the way we would debug a program step by step today. In order to do this, you need to keep track of three things: a snapshot of the tape, where the printer scanner is located on the tape, and the state of mind of the automatic computing machine. Turing's notation was a snapshot of the tape, like this one. Then underneath of that, he would mark the position of the printer scanner with the name of the current state of mind of the automatic computing machine. This example shows the symbols that are on the tape and that the printer scanner is located on the square with an X in it, and that the state of mind of the automatic computing machine is P. This, along with the states of mind table, is all you need to run an automatic computing machine. In this example, the printer prints a blank, that is, erases the X, because that is where the printer scanner is located. Then it moves to the right one square and finally ends up in the Q state of mind. And we end up with, using Turing's notation again, a snapshot of the tape with a Q underneath the last 0, that is the one furthest to the right on the tape. This process is repeated over and over to produce the output of the automatic computing machine. Now, let's start from the beginning and run the automatic computing machine that generates the expanding one sequence. It starts with a blank tape and the machine in a B state of mind. We look at the table of states of mind and see that in the state of mind B, when a blank is scanned, the printer scanner prints a schwa, moves to the right, prints a schwa, then moves to the right again, then prints a 0, then moves to the right twice, then prints a 0, then moves to the left twice. Then underneath the leftmost 0, we see an O character, because that is the new state of mind for the automatic computing machine. And this continues as we write out a new snapshot of the tape each time the automatic computing machine completes a direction. Turing used this example to show that his automatic computing machine could make use of memory. Let's run this example up to the point where it starts to use memory. You can see the automatic computing machine is moving along the tape and through the various states of mind and beginning to build up a subsequence of ones. At this point, it has built up the first subsequence of 1, and that's just a single 1 symbol. What it's going to do next is copy that sequence of 1s to the end of the tape, but add another one to it, so that it makes a subsequence of 2 1s. To do this, it marks all of the 1s in the subsequence it just made with X's, in this case just 1. Then it moves to the end of the tape after that 0 it previously printed and prints a 1. That is the first 1 of the second subsequence on the tape. Then it moves to the left, and each time it finds an X, it prints a blank over it, that is, it erases it, and then moves to the end of the tape and prints a 1. This is how it copies the 1s from the previous subsequence. Notice that it used memory to keep track of which ones to copy. Eventually, there are no more X's, and the automatic computing machine finds this out because it runs into a schwa character, at which time it moves to the end of the tape and writes a 0, then starts the process all over again. Let's let it run through a couple more subsequences now that we've seen the details of how it works. Now it's completed a subsequence of 3 ones. And now it's completed 4 ones, and so on and on and on. Now, we've just seen a computing machine run. It's an automatic computing machine that just does one thing: compute those expanding subsequences of ones. To get a different sequence, we would need a different automatic computing machine. Of course, the only thing that would be different from this one would be the set of directions that it followed. That's not like the kinds of computers we're used to using today. You don't have one computer to browse the web and another one to do word processing. You expect your computer to be a browser when you need a browser and a word processor when you need a word processor. This was a problem for Turing, too. What he needed was a single automatic computing machine that could compute all possible satisfactory sequences of zeros and ones that could possibly be produced by automatic computing machines. A single computing machine means producing all of the possible sequences with just a single table of states of mind. He called this kind of automatic computing machine a universal computing machine. He then used that automatic computing machine to determine if there were any real numbers that a computing machine could not compute and solve the Entscheidungsproblem. But how do you do this if all we've seen so far are automatic computing machines that produce just one specific sequence? There is at least a conceptual way to do this, which Turing turned into reality. We make an automatic computing machine that can scan a table of states of mind. It would work like this. Instead of starting with a blank tape, we write the table of states of mind, like the one in the previous example, onto the tape in a linear fashion, using a semicolon to divide one line from the other. Next, we write the table of states of mind for that automatic computing machine that will do the scanning. That'll be a problem, but we'll get to that shortly. What we expect to happen is that the automatic computing machine scans the table on the tape and then produces the expanding one sequence we saw earlier. If we wrote a different table of states of mind onto the tape, we would expect to get the sequence of zeros and ones that table produces. There are a couple of ways of looking at what is going on here. One is to say that our automatic computing machine is emulating another automatic computing machine. Or we could say that our automatic computing machine is reading in a program and executing it. In any case, what Turing came up with 80 years ago is how computers work to this day. But to make that universal computing machine actually work, we're going to have to write out the table of states of mind for it. We can start like we did in the previous example and name the first state of mind B. Now comes the problem. We have to write down the name of the symbol this direction scans. But we don't know what is in the tables on the tape. After all, this automatic computing machine is supposed to be universal. We could do something like what was done for the original version of BASIC, in that you are only allowed 26 different names for variables, the letters A through Z. But how do we know if this would be sufficient for writing out all the tables of states of mind that were possible? Well, we don't, and in fact, there is no reason to think that just 26 symbols would be enough. Turing's solution to this problem was incredibly insightful. Rather than putting the table of states of mind directly onto the tape, he came up with an alternate representation of a table of states of mind, which he called a standard description, or S.D. And he restricted the operational capabilities of his automatic computing machine to just 3 kinds of directions. Later in the course, we'll go into the details of those directions and how the standard description is created. But here is the standard description for our expanding ones table of states of mind, or at least as much of it as will fit on the screen. When you look at this, I'm pretty sure your first thought is something like, wow, that's pretty inscrutable. However, if you took the archetype first program, Hello World, in your favorite language, then looked at what was actually loaded into your computer's memory for the computer to execute, I think you would find that pretty inscrutable too. The value of the standard description is that with just 7 different symbols, D, C, A, N, L, R, and semicolon, you can represent any table of states of mind. Because there is a finite, known list of symbols involved, you can solve the problem of not knowing what symbol might be used in a table on the tape. And that's just what Turing did. He created a table of states of mind that could scan a standard description and produce the output of the table of states of mind that standard description represented. Later in the course, we'll be looking at the table of states of mind for the universal computing machine and how Turing went about creating it. So what Turing realized was that the language he used to write his programs had to be something humans could comprehend, but then it would have to be translated into a language his universal computing machine could comprehend to be able to run it. And to this day, we are using that same general process when we write our programs. Now, we've seen a 20,000-foot view of uncomputable numbers. Alan Turing wanted to understand how computers, the human ones that is, computed real numbers and what their capabilities were. Along the way, he cleared up some questions about the logical basis of mathematics and invented a model of computation, his automatic computing machine, that is still valid today and is still the benchmark for the computational capabilities of all computers. That's pretty amazing for something done 80 years ago by someone who did all their programming with a fountain pen. The rest of this course will go into the details of Turing's automatic computing machine, the things he found out from them, how his proofs worked, and the pragmatic and theoretical concepts that Turing introduced 80 years ago and that are still employed in programming to this day.